Okay, can the chat hear me? Wonderful, thanks. Okay, so as always, remember to do your seating survey. Just before class started here, there was a giant pop from the projector over on this side, suggesting that maybe one of the bulbs went out. And I think that side looks dim compared to this side. If you are having trouble seeing because of that, there are empty seats over here if you want to switch to a different seat. Up to you. Just make sure you record which seat you're actually in when you are doing the seating survey. Okay, so yesterday afternoon was something of an exercise in frustration for me, and I want to go through a little bit of why that was. There are lots of people that were trying to get in touch with me individually about issues with the group activity that was due. And I was on Piazza answering questions, private questions and public questions, pretty much all afternoon. Felt like I'd gotten through everything, and then I went over to my email and found a bunch of questions there as well. There's a reason why I ask you to contact me through Piazza. It's so that all the information that I'm dealing with is in one place, so that I can go through and answer questions in one place and make sure that I'm getting to everything. As a reminder, you can post anonymously. Also as a reminder, you can send me a private message on Piazza just by selecting that the target is an individual instructor. So it's just as private, just as FERPA compliant as email is. It's just, it allows me to have one place that I have to go to work with students rather tthan having to manage multiple places at once. So please, please do things on Piazza. So why was yesterday afternoon such a frustration? It was because there were apparently a lot of groups that had not been able to get in touch with each other before. There were some group members that submitted the only one submission from the group without talking to other group members before doing it. There were several people that said, I only found out that this thing was due a few hours before it was due, despite the fact that there were multiple Piazza posts about it. There were announcements in class daily about it. The calendar and the grade book in Blackboard have it listed there. I don't know how much clearer I could have been about what the due dates were that were coming up. So the place to voice your dissatisfaction with the communication that you had with your group members is in the quiz that's due today. At the very end, there's an ungraded question that says, tell me anything that you think I should know about your experience of doing this group activity. I'm going to be including that in every one of these quizzes, so you're always going to have an opportunity to tell me somebody didn't work on this, somebody didn't contribute, or somebody submitted this before even talking to me about submission, that sort of thing. And what I'm going to do Thursday, after today, is I'm going to adjust group membership based on the responses that I get from this. So if there are non-responsive group members that didn't pull their weight, well, I'm going to take them out of their current groups and I'm going to put them together. Okay, and so that's going to just be a consequence of not having been responsive. Proactive group members that were trying to get things done but were frustrated by dealing with the with non-responsive group members, well, those people are going to get put in a group together, and hopefully multiple proactive people working together are going to have a good experience with it. And remember, I can see your discussion board posts, so I can tell whether or not you have been reaching out through the discussion board to try to communicate with your group. I had several cases where people were saying, nobody tried to contact me. And I went in and looked at the discussion board and saw that, you know, a week ago, everyone except this one person posted on the discussion board. So I can tell what's going on with these things. So this shuffling is going to be happening tomorrow based upon the responses I get on these quizzes. Going forward, they're not going, after this activity, yes? I'm sorry, I'm having trouble hearing you. If you have a solid group that is working well, and if that's what I hear in the responses to the quizzes, I'm not going to mess with success. So yeah, you can stay with the group that's already working well for you. So going forward, after this particular activity, no individual submissions. You're going to work with a group, period. Okay. There's only one submission per group. So if you end up submitting without consulting your group, then you get a 0. If you don't participate and hold up submission until really late due to lack of communication or lack of work on it, you get a 0. Okay. These group activities I view as being the way to solidify your understanding of complicated material, and doing that as part of a group with back and forth with members of the group is part of how that works. So I view these very seriously. I'm going to be evaluating each of these things on a case-by-case basis using the quiz responses. Okay, any questions on this, on how the small group activities are going to work from here on out? Okay, I apologize for sounding frustrated. I had hoped yesterday afternoon to be able to write the first exam so that I would then have time to take the writing of the first exam and have time to come up with a study guide or a practice exam or something based on it. But I worked pretty much straight through trying to address these problems almost entirely due to people not having even tried to communicate with their groups until yesterday afternoon, and then finding, oh, they're not communicating. So that's why I'm frustrated. And unfortunately, what it means is I'm not able to get things to you guys that were doing it right as much as I would like to. So that's my frustration. All right, I think there was a hand. Was there a question? A question on content videos, okay. So being able to go back and see the content videos. So they're still available. I think you should be able, under the content videos list, they should still be listed there, right? Yeah. And remember that there's a YouTube link underneath the main link, which takes you to a version of it that doesn't have the embedded quizzes. So you don't have to sit through and try a new submission of the quiz thing. So yes, you will have access to those all the way through the semester. Okay, upcoming deadlines. Today at 5 o'clock, the content video quizzes. And then the small group activity quiz, which is individual. So the Google Doc that you guys were working on, there is one submission on for the entire group. These quizzes you individually do based on your understanding. Going to be where the grading of your performance happens, and I'm going to be spot checking. Okay, do the answers correspond to what was on the in the Google Doc? Is the Google Doc actually complete? Those sorts of things. That's the purpose of the Google Doc. Okay. Friday is homework number 3, and then Tuesday of next week is small group activity number 2. I request that you don't start doing too much coordination on that until after tomorrow, after Thursday, because tomorrow is when I'm going to be doing any of this shuffling that I'm doing in order to make sure that, that group dynamics are working a little bit better. Okay. Any logistical stuff before we get to muddiest points? Yes. Is there a way to get what posted? Notifications from the discussion board. That's an interesting question. I think you can subscribe to a thread on the discussion board, but that's not something I've tried personally. Does anybody here have any experience with that? Okay. If you would send me or post on that question on Piazza, either privately to me or just open, and that will be a reminder after class for me to go in and try to find an answer to that for you. Okay, so let's do some muddiest points. So the first one that we had, this was actually one left over from yesterday because we weren't able to get to all of them. What mass of ice can melt at 0 degrees provided 275 kilojoules of energy given a delta H of fusion. Okay, so this is one of the two kinds of heat transfer kinds of questions. Because you are looking at a phase transition, what you generally want to do is write out what the process is that you're looking at. So we have H2O solid goes to H2O liquid. And this has a delta H of fusion of 6.01 kilojoules per mole. So you can figure this out largely by just dimensional analysis. You have a delta H of fusion, which is kilojoules per mole, and you have an amount of energy. So if we have 6.01 kilojoules per mole, and we want to do something with this to get our 250.0 kilojoules, then we're going to need to multiply by how the number of moles of water we have. So N of water. So moles of water cancel, you're going to end up with getting kilojoules, right? So if we do that, we can divide through 250 divided by 6.01. So our number of moles of water will be, if somebody have a calculator? I can probably pull one up on my phone, I guess. 250 divided by 6.01. We get 41.6, 60 moles. Well, if we have a number of moles, how do we get to grams of water? Because they ask for what mass of ice. We use the molar mass. So 41.60 moles of water. We know that molar mass is grams per mole. So if we do it like this, then our moles are going to cancel. And this is, if I remember correctly, 18. And if you need more significant digits, you can look up what the extra significant digits are. And so our 41.6 times 18, we get 748.8 grams of water. Okay. Sorry, I did that off screen. So this is one of those, this is straight from the thermochemistry section of Chem 111. You have the delta H for a reaction, and you have you're either given the amount of heat that is used, or you are given the mass of the amount of material that you have, and you just convert from one to the other, straight from 111 stuff. Any questions on this kind of problem? Yes? Where did you get 250 from? Where did I get 250? That was part of the question. Oh, I mistyped, I miswrote 275 based on the question. So the number's wrong. I apologize for that. But the procedure's the same. Is that okay? All right. Okay. The second question here. Heat released by cooling 54.0 grams of water from 57 degrees C to -3 degrees C, and given 3 pieces of information. Okay, here we are combining multiple steps, and so we have to treat those steps separately. To visualize what's going on, let's think about this as a cooling curve, okay? Just so that we can identify what the various processes that are going on are. So we are starting at 57 degrees C. And so what kind of water is that at that point? Is it gas, liquid, or solid? Liquid. And so we are going to cool that to some point. When are we going to be done cooling the liquid water? At what temperature? 0 degrees. Okay. Then it is going to freeze. And that freezing happens at a constant temperature. Then, once it is all frozen, it is going to decrease in temperature until we are at -3 degrees C. So this is a 3-step process, so we're going to have to calculate 3 different heat transfers, and then add them together. So let's call this step A, this step B, and this step C. So what do we do for A? Yes?
Use Q equals M times C times the change in temperature.
Right. So what we do is we use Q equals the heat capacity of the substance, of the material, times our delta T. And our heat capacity here is the mass of the material times the specific heat of it. Okay. So we know our delta T, 57 degrees C. We know our mass, which is 54.0 grams of H2O. And we know our specific heat for the liquid is 4.184 joules per gram degree C. So we multiply those 3 things together. And we get our Q is 12,880 joules, or 12.88 kilojoules. All right. Part B. This is just like what we did here, just with a different unknown. Okay. So we have our mass is 54.0 grams of water. We need to convert this to moles because our delta H of fusion is in kilojoules per mole. So we need to have grams of water in the denominator so that the grams will cancel. So we're going to have moles in the numerator. And so we have 18 grams of water per mole of water. Now we multiply that by our 6.01 kilojoules per mole of water for the heat of fusion. Grams of water cancel, moles of water cancel, and you're left with kilojoules. So 54 divided by 18 times 6.01 gives us 18.03 kilojoules for step B, excuse me. Is step C going to be more like step A or more like step B? Step A. We have a single substance and we are changing its temperature. So Q equals C delta T, where C here is the mass times the specific heat. The delta T in this case is going to be 3 degrees C. Our specific heat is going to be the specific heat for ice, which is 2.09 joules per gram degree C. Our mass is still the same at 54.0 grams of water. So we multiply the three things together. (54) times 2.09 times 3, and we get 339 joules. And since the others are all in kilojoules, that would be 0.339 kilojoules. You now add the three together to find out the heat transfer that's associated with the entire three-step process. I'm going to assume you can add three numbers. Yes?
Dana asked if there's a negative sign for part C.
All right, so the signs can get confusing, and that's one reason I tend to not put them in, because it's better, in my opinion, to look at it from the perspective of, is heat being released or is heat being absorbed? Okay. If we look at our cooling curve, we are, the system is going down in energy over this entire process, so heat is being released the entire time. And so from the perspective of the sample, all three of these Q's are negative. Okay. From the perspective of the environment, all three of the Q's are positive because heat is going into the environment. Okay. If you want to see where that comes from mathematically, this delta T is actually negative because our final temperature is 0, our initial temperature is 57, and so you're going to have a negative delta T. Same thing here, our final temperature is -3, our initial temperature is 0, so you're going to have a negative delta T as you go through this. In the middle step, where it comes in is that the heat of fusion, this 6.01 kilojoules per mole, is for the melting process. It's going to be negative if you're doing it for the freezing process. Okay. But in my opinion, it is better as you get to the end of the problem to look at the magnitude of the numbers and think, should this be negative, should this be positive at that point, based on whether the system is going down in energy or the system is going up in energy. It just helps keep things straight. Okay. Okay, any questions on this kind of process? Yes? Adding them. So you release, Q sub A amount of heat in step A, Q sub B in step B, and Q sub C in step C. If you want to know the total amount of heat that is released, it is just the sum of those 3 steps. Now, of course, this can be extended even further. You could start in the gas phase, go through condensation, and go through freezing, so that you would then have as many as 5 steps in the process: the cooling of the gas, the condensation, the cooling of the liquid, the freezing, the cooling of the solid, or vice versa. But it's conceptually no harder. It's just a couple extra steps. Okay. So this is a question from the small group activity. If water freezes from the top down, wouldn't this be true? In a pool of surface water that partially freezes, the frozen portion of the water will block access to the submerged minerals. So this is talking about the idea of having a pond or a puddle or something where there are submerged minerals at the base here. And wouldn't freezing at the top to make a layer of ice on the top, wouldn't that prevent access to those minerals? Well, the question is access from what? Because the things that we're looking at are potential prebiotic chemical reactions of stuff that's dissolved in the water. So what we're looking at are things that are dissolved in the water down here. So those things still have access to the minerals. Whereas if we had a different solvent, some kind of solvent that froze from the bottom up, then you're going to end up with a frozen layer down here. Then anything that's dissolved in that solvent is not going to have access to those minerals. Oops, I keep going off the bottom of the screen. I apologize for that. Does that generally make some sense? So water is really unusual in that it has that its solid form has a lower density than its liquid form. One of the benefits of that is that in this kind of scenario, the ice floats, leaving aqueous access to the minerals that are down on the bottom. Okay. Okay. There's a question about finding the entropy change for dissolution of copper 2 sulfate. And so we have not done a really in-depth introduction to entropy yet. That's going to be coming up before too much longer. But we're generally describing it as a measure of the amount of disorder, or how many different arrangements the system could be in. So a good analogy for this kind of thing is a deck of cards. If you have a deck of cards that you just opened up, opened up the plastic packaging on, all of the cards are in order. Ace through king, and then I think they usually reverse it, king through ace, something like that. But there's a specific order that the cards are always in when you open it. You shuffle the cards, and you will effectively never spontaneously get back to that ordered system. And so the entropy of a disordered deck of cards is higher than the entropy of the ordered deck of cards. So now, how do we apply that concept to dissolution? Well, if we start with a crystalline block of our copper 2 sulfate, then what we have here is an ordered arrangement of the anions through the whole thing, and the cations in some regular crystal structure. And that's a very ordered kind of system. That's analogous to our stock ordering of the deck of cards. If we then put this into a beaker of water, and we now have the anions floating around, and we have the cations floating around, there are all kinds of different positions each individual ion could be in, because and in fact, they are interchanging their positions on a pretty regular basis because they're mobile. They float around. So the disorder of this system is going to be much higher than the disorder of this system. So the process of going here, which we can write as this, the process is going to cause an increase in disorder or an increase in entropy, so that delta S is going to be greater than 0. Now, we haven't gone into yet calculating the actual value for delta S, and we haven't gotten into exactly what's the relationship between this entropy thing and disorder is. We are going to get to those topics. But this is the level of understanding that I'm looking for at this point, is simply you're going from a state that is highly ordered, a crystal is highly ordered, to a state that is highly disordered because there's a lot of different possible arrangements that are, from our perspective, from our bulk perspective, seem equivalent. It doesn't matter where any individual ion is. Okay? And how we use this is looking at spontaneity. So if we come down here, the two indicators of spontaneity are if delta S is greater than 0, so an increase in entropy, or if delta H is less than 0, meaning that it is an exothermic process. So if delta S were 0, then an exothermic process would be spontaneous. If delta H were 0, so neither endothermic nor exothermic, an energy neutral process, then any process that has an increase in entropy will be spontaneous. And similarly, if both delta S is greater than 0 and delta H is less than 0, both the indicators are pointing the same way, then that reaction will always be spontaneous. So a good example of that would be the burning of gasoline. Okay. Gasoline, burning of gasoline is clearly an exothermic process. We know that it releases heat to the environment when it happens. And you are taking a small number of molecules, octane in particular, in the gasoline, and are creating a larger number of molecules, the CO2 and the H2O, that are in the atmosphere, that are the gaseous release products. So there are more ways to arrange a bunch of molecules than there are to arrange a fewer number of molecules. So that is an example where delta S is greater than 0 and delta H is less than 0. And so the burning of octane is spontaneous. Contrariwise, if delta S is less than 0 and delta H is greater than 0, that is a reaction that will never be spontaneous. It simply will not happen. And so the taking CO2 and water vapor and then bringing them together to form octane and atmospheric oxygen, the reverse of the reaction we were just talking about, will never be spontaneous. Okay. The trick is coming in, the trick is when these two point towards different answers for spontaneity. So if you have delta S is greater than 0 and delta H is greater than 0, well, then there are going to be some temperatures at which it's spontaneous and other temperatures at which it's not. Similarly, delta S less than 0 and delta H less than 0, there will be some temperatures at which it's spontaneous and other temperatures where it is not. We will get into how to tell what that temperature is in a future chapter when we talk more about entropy. The main thing to look at here in terms of the context of solution formation is that the process of dissolution always has delta S greater than 0 if your solute is a solid. Okay, so it's looking at the delta H then would be the unknown thing that you're looking at to try to determine whether it's going to be a spontaneous process or not. Now, I've mentioned that if it's a solid. Remember, you can dissolve gases into a solution. So how can I can't talk. How can fish breathe? Because there's dissolved oxygen in the water. Okay? But taking oxygen molecules from the atmosphere and dissolving them into water under certain conditions may be a decrease in entropy because there are more ways it can be arranged out in the gas phase. So, so it does take some thinking about the system to determine which direction the delta S is and which direction the delta H is. Any clarifying questions on this topic? Okay. All right. An amalgam of mercury and gold, which can have a range of concentrations, is a solution. And this is from the one of the content video quizzes. The answer is true, but why? It sounds like the different concentrations would at least affect the composition or dispersion of the compound. Let's think about this from the perspective of an analogy to a solution we're all more familiar with, say salt water. Okay. If you have a little bit of salt in water in one sample and a lot of salt in water in a second sample, they're going to have somewhat different properties. They will conduct electricity to different degrees. They will have different densities. There will be some differences between them. What makes it a solution rather than a compound, so notice here that at least affect the dispersion of the compound. What makes it a solution and not a compound is that you can continuously vary the concentration. It's unlike water itself, which has 2 hydrogen atoms for every oxygen atom. There is nothing that specifies how many sodium chloride units you will have in salt water relative to how much water you have. You can continuously change that ratio. And so it is a solution instead of a compound. The same thing is true with an amalgam of mercury and gold. There is, you are not forming something that is, say, mercury 2, gold 3, or something like that. That's not what we're doing. We can continuously vary the ratio of mercury to gold, which makes the combination of the two a solution rather than a compound. And yes, changing the composition will change the properties somewhat, but it's continuously changing, not suddenly now it's a different material. Okay. Are we cool with that? All right. Okay, why are there 3 moles of ions if only 1 mole of potassium sulfate dissolves in water? Okay. So the first thing to do in looking at this kind of question is to remind ourselves what potassium sulfate is. So we know we have potassium, we know we have sulfate. Now, what is the ionic charge on a sulfate ion? Does anybody remember that? -2. So I'm going to put a -2 here as a reminder. What is the ionic charge on a potassium ion? +1. So in order for this to be a charge-balanced compound, we have to have this be K2SO4. Okay? Now, when this dissolves, We will write this as K2SO4 aqueous, but this is really shorthand. What this side here, K2SO4 aqueous, means is 2K plus aqueous plus SO4 2 minus, 21, 2 minus aqueous. This is shorthand for this. When you dissolve an ionic compound, the ions separate from each other. So every mole of K2SO4 that dissolves will result in 2 moles of potassium ions and 1 mole of sulfate ions, for a total of 3 moles of ions. Does that make some sense? Any clarifying questions on that? Okay. Last question from the muddiest points for today was calculating the density for different types of unit cells. So we've gone over this several times. I'm going to outline the idea. If somebody wants me to go into extreme detail on one of these, we can have a follow-up question to do that. But the general idea is, so we want to calculate density for different types of unit cells. So the first thing we need to do is know what density is. Can somebody give me an explanation of density? Mass per volume, that's right. So mass per volume. Now, does it matter how big our sample is when we are looking at the density? So if we have a giant block of let's say, nickel versus a tiny shard of nickel, no, they should have the same density. The way we can see that is that if we double the size of our sample, we double its mass, but we also double its volume, and the two things cancel, so the density ends up being the same. So that means when we're trying to do this calculation, we can pick any size that is convenient. And since we're talking about unit cells, picking a single unit cell is probably the most convenient thing we can do. So let's take a look at a unit cell. And why don't we, for grins, pick face-centered cubic as the one we're looking at. And I'm doing a horrible job of drawing this. I apologize, because those things should be touching. Okay, looking at face-centered cubic. We need to find out the mass that is in that cube and the volume that is in that cube. So, how do you think we might find the mass? Yes?
Would it be dependent on what type of atoms in it?
Sure. So let's say, I don't remember which ones are actually face-centered cubic. Let's pretend it's gold that we're dealing with. I think those may be face-centered cubic. So gold. What is the, how does that help us determine the mass of one of these? Well, the molar mass, we're going to use that, absolutely, yes?
Well, it has 4 gold atoms in it, right?
Right, we need to know how many gold atoms are in the unit cell. So we see that there is 1 gold atom at each corner, so there are 8 corners, but each one is only 1/8 in that unit cell because it's equally in 7 others, so that's going to be 8 times 1/8. But for face-centered cubic, we also have an atom on the center of each face that is halfway in the unit cell. So how many faces are on a cube? 6. And each one is halfway in there. So this becomes 1, this becomes 3. Oops, there we go. This becomes 1, that becomes 3, for a total of 4 atoms in that unit cell. So now we figure out what is the mass of 4 gold atoms. So this is dimensional analysis. Start with what, so I mentioned this yesterday, but I know different people come to different class periods. There are enough questions coming up on Piazza and in classes that are essentially straight dimensional analysis questions that I figured that sort of a review of dimensional analysis might be useful. And so I put together a video on that topic, which I will be using when I teach 111 next time. And I've given you guys access to it. There are no quizzes associated with it. It's just there for your benefit should you want to do it. The way to think about dimensional analysis is a 4-step process. 1, start with what you know. 2, multiply by 1. 3, repeat step 2 as needed. And 4, arrive at the answer. Now, when I write dimensional analysis like this, steps 2 and 3 together sound completely useless, and step 4 sounds like magic. But what I hope to convince you is that careful, clever use of step 2 can turn this into an extremely powerful tool. So let's think for a minute about what we mean by multiplying by 1. We can write 1 in a variety of different ways. So an example where you already know how this could be useful is imagine you have 3/4 of something and you're trying to add it to 1/8 of something. You need a common denominator, right? So to do that, you multiply this by 1 in the form of 2/2. It doesn't change the value of this quantity, but it expresses it in a way that becomes more useful for this application. Now, the cool thing is that the numerators and the denominators don't have to be in the same units. So imagine you have 12 feet of rope, and you want to know how many inches that is. Now, ignore the fact that you already know, just multiply by 12, okay? Let's see how we would figure that out. We know that 1 foot equals 12 inches. Let's divide both sides of this by 1 foot. 1 foot cancels with 1 foot, and this equals 1. That means we can multiply by this thing without changing what we're looking at. So that means that if we take 12 feet, multiply it by 12 inches over 1 foot, feet and foot cancel, and we now end up with 144 inches. That is all dimensional analysis is. It is starting with what you know, multiplying by 1 cleverly so that units cancel, and you keep doing that until you arrive at your answer. That is exactly what we're going to do here. So we know we have 4 atoms of gold. Okay. Now, we need to get out of atoms. What can we get from atoms to that might be useful? Avogadro's number. So that's going to let us convert from atoms to moles. Okay, so remember that 1 mole of anything, in this case gold, is equal to 6.022 times 10 to the 23rd atoms of gold. So we're going to use this as our conversion factor. We want atoms to cancel, so we need this part in the denominator. 6.022 times 10 to the 23rd atoms gold, 1 mole of gold. And atoms of gold cancel, we now have moles. But we're targeting mass, right? How do we get from moles to mass? Use the molar mass, right. So we want moles to cancel, so this is going to be multiplied by something where you have moles of gold in the denominator, grams of gold in the numerator. The molar mass of gold is, I've got a periodic table somewhere. Pull it out? Yes, I did. Molar mass of gold is, oh, my resolution sucks. It looks like 194, 196, I don't know, something like that. 197?
Yeah, that's about it.
Okay, so 197 grams of gold per 1 mole of gold. So moles of gold cancel, and you end up with whatever our number is here. I'm going to assume you can plug that into a calculator. You're going to end up with something in grams of gold, and that is now going to be your numerator. Volume. Well, we are talking about 1 unit cell, so it's going to be whatever the edge length is cubed. That's simply the definition of volume for a cube is the edge length cubed. Okay. How do you find the edge length? Well, you have to do a little bit of geometry. You have to notice that the atoms are touching across a face diagonal, and so from here to here is 1 radius of the gold atom. From here to here is 1 radius of a gold atom. From here to here is 2 radiuses of a gold atom, because it goes to the center and then out to the other side. So the diagonal here, the face diagonal, is going to be 4 times the radius of the atom. And then you just use Pythagorean theorem, because this is a right triangle, to find the edge length in terms of that diameter. So you do that geometry calculation, and you'll have your denominator probably in something like cubic picometers. And since normally we do densities in something like grams per cubic centimeter, you'll then have to convert whatever units you had from picometers to centimeters. And you do that exactly like what I was describing here for dimensional analysis. For each one of the picometers, you find your conversion factor to centimeters. So that's the procedure you go through to calculate a density from information of a single unit cell. Yes?
So we'll never have to calculate density of like a hexagonal unit cell.
I'm not going to ask you that one, no. Yeah, the main thing to know, okay, well, the packing density of hexagonal close packing is identical to the packing density of face-centered cubic. So you could just say, I'm going to pretend it's face-centered cubic, and I'll do the calculation there, and the answer is going to be the same because it's packing the same density. But that's kind of an extra step that I don't know that there's a point to ask you. Any clarifying questions on any of this? Okay, we've made it through our list of the muddiest points that were up on Piazza, so I will throw open the floor and the chat to answering any questions anybody has. We have about 15 minutes left in class. Yes? Have I figured out how the test is going to be administered? I was hoping to figure that out yesterday afternoon, but I didn't. I am very, very strongly leaning in the direction of having the test be entirely open note, open book, open resource. Because I think that all of these mechanisms to proctor remotely and this sort of thing is really just, it adds more stress without adding any clear benefit. Now, what that means is that the questions I'm going to be asking you are not going to be, can you look up this detail? Because, of course, you can look up that detail. I'm going to be asking you about kind of extending your knowledge a little bit, taking the processes that we've talked about and the relationships we've talked about, and then applying it to a new scenario. So, for example, find a blank sheet of paper. Let's suppose that I tell you that a certain compound, a certain ionic compound, AB, where A is our positive cation, B is our negative anion. Which tends to be bigger, the anion or the cation? The anion. You add electrons to it, it expands the shell. You take electrons away, the shell shrinks because there's less electron-electron repulsion. So let's suppose that the B's form a simple cubic arrangement. Now there are holes inside this, right? Which is where the A's are going to fit. So I could ask you something like, if the A's fit in the octahedral hole that would be right dead center in this lattice, what is the largest cation A that would be able to fit there without expanding the matrix, expanding the lattice, making the corner ions push away from each other? Okay. That is not a problem that we have directly solved here in this class, but solving it doesn't require any skills that you have not practiced multiple times. You just have to think about the geometry, figure out where the points of contact are going to be, so that you can look at the geometry and figure out where the atom would be, or figure out what size of atom will fit. So, so this is the kind of thing where I'm not giving you something that that you just look up. I'm not giving you something where, yeah, I have an example that does exactly the same thing, it's just there are different numbers in it, I'm going to follow that. This kind of question is asking, do you understand the principles that we've been discussing, and can you apply them? That's the kind of question I'm going to be targeting. Now, because of that, these are, in some sense, harder questions. And so there will be fewer questions on this exam than you may be used to. This is not going to be a 100-question multiple choice exam kind of thing, okay? And my hope would be that I would be able to give you one sort of unit cell lattice type kind of system, and then ask you multiple questions about that one. So you only have to really be constructing your understanding on that one system, but then I can ask multiple things about it to get at different pieces of information in the question. Does that generally make some sense? So I am, it is going to be an online exam because nobody wants to, in the age of COVID, nobody wants to have to deal with physical proctoring. I have not yet figured out if I'm going to be doing it as a Blackboard test or a Newton test, but I don't know that that's going to matter too much. While I do think I'm going to have like a time limit on it for, you start it and then need to be done within a certain period, I'm going to be kind of lenient on that. If I look at it and say, that ought to be about 2 hours worth of work, I'll say, okay, you can have 4 hours so that nobody's feeling the time crunch on the thing. And I'm also planning, I hope, to be able to give you like a 3-day period or something that you do it whenever is convenient for you over that 3 days. That's my current thinking, but because I haven't been able to go through the process of really laying out this is what I'm going to do, don't take any of that as a promise yet, but that's what I'm trying to figure out and hopefully we'll have resolved before. My goal is on the weekly announcement, what to expect in the upcoming weeks thing that I send out this Friday. I'm hopeful to be able to lay out in that exactly how it's going to work. Any clarifying questions on that or moving on to another topic? Yes.
So for the individual quiz, not the group project, if you got, like, there was a lot of them where you had to select multiple boxes, and if you got, like, say, like 4 out of 5 right, do you miss all 10 points, or do you get, like, 8 out of 10 points, or how does that work?
Yeah, it's a good question. So on the individual quizzes where that you select multiple things, if you get like 8 out of 10 right or something, do you get any credit at all? I don't remember how I set that up. So I'm going to have to go back in and look. I think, the way I want to have set it up is that it is for you to get partial credit. I don't know if I did. And so if Blackboard will let me, I will go back in and change how that is graded. I will look at that because I prefer to be able to give you partial credit.
Thank you.
Yeah. Yes.
The whole like dissolve thing. Do the solution or the solvent and solvent have the exact same intermolecular forces, or do they share like one in common?
Okay, so the question was for the whole like dissolves, let's see if I can talk. The whole like dissolves like thing is the, for the whole like dissolves like thing, does that mean do all of the intermolecular forces have to line up, or is having 1 or 2 in common going to be sufficient for them to dissolve? Generally, the idea is you want the preponderance of them to line up. So if you look at oil and water, for example, the oily molecules will almost entirely just have London dispersion forces. Water has London dispersion forces, but the hydrogen bonding and the dipole-dipole interactions are really strong in water. And so as a result of that, the oil and water won't mix, not because of the oil, but because of the water. Because in order to pull 2 water molecules apart, you have to intersperse something in between them that can make up for the energy cost associated with pulling them apart. So then you look at something like dimethyl ether. So you have a CH3, an oxygen, and a CH3. Okay? That molecule by itself cannot hydrogen bond because there are no hydrogen bond donors in it. It does have a dipole, but it's not the strongest dipole around. And so that molecule will dissolve in something like an oil, like an octane. Okay? But the oxygen can act as a hydrogen bond acceptor. So if you try to mix that dimethyl ether into water, it will dissolve there too, because it can accept hydrogen bonds and can therefore intersperse itself between water molecules and replace the strong hydrogen bonds that water had for itself with hydrogen bonds to the dimethyl ether. So does that make some sense? So it's not a hard and fast rule. It's more a question of tendencies. And further, it's not there is not a hard and fast, it dissolves, no it doesn't. Because generally something will dissolve over a concentration range. And then beyond that range, no more will dissolve in it. So even something like oil and water, there will be a few, very small number, but a few oil molecules that will manage to get into the water phase. Not much, but when you get down to part per billion kinds of levels, yeah, you can see a tiny little bit in there. So, so this whole like dissolves like thing is really more a question of thinking about what's your list of intermolecular forces, compared to something else, does this have more similarity or less similarity? So you can get sort of relative solubilities that way. Does that help a little bit? Okay. Anything else? We have about 4 minutes left. Yes? Go over the problem that I put there, okay? So, if we think about the cation that's going to be down here dead center into this, where do we think that contact point is going to be? Let me shrink the view of this. Like that. And we are putting our cation dead center here. Okay. Now this cation, is that going to be equidistant from all 8 of the corners?
Can you switch your?
Oh, yeah. Thank you. Yes. Let me switch this so, there we go. All right. So is this cation going to be equidistant from all 8 of the corners? Yes. Okay. So if we, so where are the the different kinds of atoms going to be touching? Along what portion of this geometry? The body diagonal. So it's going to go through the body across there. So for this kind of problem, you would have to be given the radius of B, right? You would then say, well, in this geometry, that's a radius of B, that's a radius of B. So our edge length here is going to be 2 RB, right? If we then say, go to a face diagonal, I'm going to draw this triangle here. This is 2RB, this is 2RB. I didn't draw it equal, I should have. This is going to be our face diagonal, so I'll do D sub F for that. And that's a right angle. So we should be able to use Pythagorean theorem to find the length of this. So 2RB squared plus 2RB squared is going to equal DF squared. Well, 2 squared is 4, so this is going to be 8 RB squared equals DF squared. And so 2 square root of 2 RB equals the face diagonal. Everybody with me to that point? Okay. Now, let's come back to this geometry here. We now have another triangle here where we have the green leg as one of the two legs, this blue one as another leg, and the red one as a third leg, right? And that's a right triangle here as well. So I'm going to draw that down here. So we've got green, blue, red, and the red is the body diagonal that we care about. So dB. So this we know is 2RB. I guess I should keep my colors consistent, 2RB. And this one we just determined is 2 square root of 2RB, right? We use Pythagoras again. So 2 square root of 2RB squared plus 2RB squared equals dB squared. So this becomes 8RB squared plus 4RB squared equals dB squared. This now is 12RB squared equals dB squared. And so dB equals 2 square root of 3RB. Okay? So that now gives us this body diagonal. Now, what does that body diagonal look like? So if we draw that whole body diagonal here, we know that we're going to have one radius of one of the blue ions, one radius of one of the blue ions there, and then the cation in the middle. So if we take our 2 square root of 3RB minus 2RB, which is this, so this is RB, this is RB, then that resulting quantity is going to be the diameter of the largest cation that can fit in that hole without expanding the surrounding network lattice of the anions. So you take that, divided by 2 to get the radius, and then you look at the candidate cation radii to see which one of them is the largest one that can fit in there. Does that general idea make some sense? Okay. So there was nothing here that's beyond what we've talked about. It's just an application to a slightly different system. Because what I'm caring about what you understand from this class is not do you remember the formula. You can always look up a formula. I want you to be able to understand the concepts and be able to apply the concepts. Okay. All right, we are out of time. Thank you very much for some very good questions today.